Okay, let's walk through this rotational motion review together. The first problem says a bowling ball of mass 7.5 kilograms with a radius 9 centimeters rolls without slipping 10 meters down a lane that is a lane at 4.3 meters per second. A, calculate the angular displacement of the ball. B, calculate the angular velocity of the bowling ball. C, calculate the radial acceleration of the ball. And then D, calculate the tangential acceleration of the bowling ball. So the first thing that I'm doing here is writing down what my variables are. I know the mass, I know the radius, I know my distance x, and I know my velocity. That's my linear velocity, is 4.3 meters per second. The next thing that I'm going to want to do is write down what I'm solving for. So for A, B, C, and D, I'm going to put a variable right next to each one of those for what I'm solving for. Angular displacement, that's going to be theta. Angular velocity, that will be omega. Radial acceleration is the same thing as centripetal acceleration, that's AC. And then finally, tangential acceleration is just A, that's linear acceleration. You might want to make a note to yourself that AC and AR mean the same thing. Alright, so for part A, I'm just using this gray table in my formula sheet here, table 8.1, that's what you want to be looking at. It's just simple relationships between linear and rotational quantities. So for part A, theta is equal to x divided by r. That would be 10 divided by 0.09 in our scenario here. And that gives us an angular displacement of 110 radians. Part B asks us for angular velocity. Again, I'm using that gray table, table 8.1 on my formula sheet, and I see that omega is equal to v divided by r. So 4.3 divided by 0.09, and I end up with 48 radians per second. So 48 radians per second is my omega. C, I'm looking for centripetal acceleration. This is the acceleration that all points have towards the center of the circle. So this would be the acceleration for each point on the bowling ball towards the center of the circle. And we learned about this in chapter 5, but I don't think this formula is on your formula sheet, so I would add it at this point. AC is equal to v squared over r. So radial acceleration, centripetal acceleration, they mean the same thing, and the equation is AC equals v squared over r. Write that down on your formula sheet. Might be useful. So in this case, 4.3 squared divided by 0.09, we get 210 meters per second squared. And then lastly, D, that's just your regular old acceleration. Now, it doesn't tell us that this is a ball that is speeding up or slowing down. It's just rolling down a lane, not rolling down a ramp. Its angular acceleration is 0. Its linear acceleration must be 0. It's not speeding up or slowing down. So D is just 0. All right, question number 2 says a wheel accelerates at a constant angular acceleration of 4.5 radians per second squared. If the angular velocity is 1 radian per second, what is the angle the wheel rotates through in 2 seconds? So in this case, if I'm looking, well, I have the angular acceleration. It's 4.5 radians per second squared. I also have my initial angular velocity, so my initial omega. And that is 1 radian per second. And then theta is what I'm looking for. That's my unknown. And my time is 2 seconds. So I'm going to go ahead and use an angular kinematic to solve this. And I only have one omega, so I'm going to have to use the only angular kinematic formula that has just the first omega in it. So the formula I'm going to use is theta is equal to omega naught times t plus 1/2 angular acceleration times t squared. So this one's pretty straightforward. I'm just going to put in my variables and solve. So when I solve, I end up with a theta of 11 radians. Pretty straightforward. All right, moving on to question number 3. Question number 3 says a Ferris wheel rotating at 20 radians per second decelerates with a constant angular acceleration of -5 radians per second squared. How many revolutions does it rotate before coming to rest? So let's write down what I know. I know my initial angular velocity is 20 radians per second. My angular acceleration is 5 radians per second squared. And I'm looking for revolutions. So really what I need to do is find theta. Because theta tells me how many radians I've revolved through, and I know that each revolution is 2 pi radians. So if I find theta and then divide by 2 pi, I will get the number of revolutions. So I'm looking for theta. So again, I need to use a kinematic. I need one without time in it because I don't have time in my little list up here. I do know the final velocity is 0 because the object's coming to rest. So the only one that I can use that doesn't involve time is that omega squared equation. So omega squared equals omega initial squared plus acceleration, or plus 2 times acceleration times theta. So I end up with 0 on the left side of the equation is equal to 20 squared plus 2 times -5, and then theta will just be my unknown. So if we go ahead and work through this, we end up with 20 squared, which is 400. We move that over to the left side, make it -400. On the right side, we end up with -10 theta. And if we divide that out, we just end up with 40 radians. But again, that's not my final answer. I now need to divide that by 2 pi to get my revolutions. Now, if you're doing this on your calculator, make sure that you put 2 pi in parentheses. If you don't, your calculator will divide by 2 and then it will multiply by pi. So make sure that you think for your calculator. Put it in parentheses, and you should get 6.4 revolutions. All right, let's check out number 4. A solid cylinder of mass 10 kilograms is pivoted around a frictionless axis through the center, which is marked O. A rope wrapped around the outer radius is 1 meter and exerts a friction force of 5 newtons to the right. A second rope wrapped around another section of the radius, which is 0.5 meters, exerts a force of 6 newtons downward. What is the angular acceleration of the cylinder? All right, we're not really concerned with over and down and up, left, right, down, up. It doesn't really matter. To us, we're looking at clockwise versus counterclockwise. And in this case, I'm going to choose clockwise to be my positive direction and counterclockwise to be my negative direction, just so that I end up with a positive torque. So that means that my variables, I have a mass of 10 kilograms, radius 1 is 1 meter, force 1 is 5 newtons, radius 2 is 0.5 meters, and force 2 should be -6 newtons. I'll correct that in a minute here. So the first thing that I need to do is figure out what my net torque is. Just like if I were finding net force, I need to find net torque because I can't figure out my angular acceleration unless I know net torque, because net torque is equal to I times alpha. So step 1, I'm going to solve for net torque. And remember again, torque is equal to R times force. So I'm looking at 2 different torques here. They have 2 different lever arms and 2 different forces. And I'm just going to subtract them. Clockwise minus counterclockwise in this case. So the first one is my force of 5 newtons times its lever arm of 1 meter. The second one is the force of -6 newtons. There's the correction. -6 newtons times the lever arm of 0.5 meters. And I end up with a net torque of 2. And that's newtons times meters. All right, so that takes the spot for torque, net torque, in my red equation up there. Now I just need to figure out what I is so that I can solve for alpha. So for I, I'm going to go look at my chart, that table of rotational inertias on the back of your formula sheet, and I see that the rotational inertia for a solid cylinder is 1/2 mr squared. That's where I got that. It's from a solid cylinder. It's on the back of your formula sheet. Check it out there. So 1/2 times our mass, which is 10 kilograms, times the radius, which we're going to use the larger radius, the radius of the entire thing, which is 1. And then I square that. So I end up with a rotational inertia about the axis of rotation of, drumroll please, 5. And that's in kilograms times meters squared. Fantastic. Now I can just take that number and stick it up into my equation with the net torque that I already found and determine my angular acceleration. So you can see it's just going to be 2/5 radians per second squared, but if we divide that out, we end up with 0.40 radians per second squared. All right, so that's it for problem number 4. Let's try another. Number 5, a hoop of radius 0.5 meters and mass 0.2 kilograms is released from rest and allowed to roll down an inclined plane. How fast is it moving after dropping a vertical distance of 3 meters? So I know my radius. My radius is 0.5 meters. My mass is 0.2 kilograms. And I know that this object is a hoop. That tells me I'm going to need to use my fancy schmancy chart of rotational inertias, and I'm going to need to know I for a hoop. I also know that I start at a height of 3 meters and I drop to a height of 0 meters. So my change in height is going to be a total of 3 meters. And then I look back at that chart and I find that I for a hoop is just mr squared. Hoops have a lot of rotational inertia. So here's my inclined plane. That's a terribly drawn inclined plane. It looks more like a step, but that's okay. At the top of my inclined plane, it tells me I start from rest, so I just have potential energy. At the bottom, I no longer have height. The hoop has rolled down the inclined plane, so I'm left with kinetic energy and rotational kinetic energy. No more potential energy. So now I can equate those two scenarios, those two sides of the situation. Potential energy, mgh, on the left, is equal to kinetic energy, 1/2 mv squared, plus rotational kinetic energy, 1/2 I omega squared, on the right. So I'm going to leave my potential energy and kinetic energy just as they are. But I'm going to substitute in what I found for I. I of a hoop is mr squared. So I'm going to put mr squared in where I have I. And remember, we know that omega is equal to v over r. So if I sub in v over r for omega squared, I end up with v squared over r squared. And now I can get rid of those r's. I have an r squared on the top and r squared on the bottom, so those cancel out. And at this point, I can also get rid of my mass. Mass cancels out, which makes my equation much simpler. I end up with GH equals 1/2 v squared plus 1/2 v squared. So now I can combine like terms and simplify this even further. GH just equals v squared. And if I take the square root of the left side of the equation, I get a great equation for v. Square root of GH equals v. So that's pretty simple. Now I just need to put in my numbers and solve. So gravity is obviously 9.8. My height was 3 meters. I'm going to take the square root of that product and end up with a velocity of 5.4 meters per second. All right, let's look at the last problem. An object's angular momentum changes by 20 kilograms times meters squared per second in 4 seconds. What magnitude of average torque acted on this object? All right, so my change in L, or change in angular momentum, is 20 kilograms times meters squared per second. My time is 4 seconds. So my net torque, that's what I'm looking for. The equation that I'm going to use is substituted from a linear equation. Remember, force times change in time equals change in momentum. So we can just sub in our angular variables and get torque times change in time equals change in angular momentum. I don't think that formula is on your formula sheet, so you should add it. Torque times change in time equals change in angular momentum. So if I flip-flop that around